All right, welcome back to differential equations. We're covering section 2.2 now, and at last we get to solve one. So, yeah, we're doing blue, very good. So here we go. These are separable equations. So here's the idea, okay, is you want to be able to separate the variables. I'll just leave it as x and y, but you want to separate the variables so that y terms grouped with a dy. Okay, so you're going to get like some kind of a g of y dy. Okay, and x terms or t terms or whatever your independent variable is, okay, are grouped with dx. Like an f of x dx. Okay, so the idea is that in the end, you're going to want a g of y dy is equal to an f of x dx, and you're going to integrate both sides, and everything is going to be happy. Okay, easier said than done. All right, now one of the first things they're going to do is show you functions that you can't do this to. Okay, isn't that delightful? So we have dx, dy by dx. Okay, let's say is equal to y plus sine x. We'll say, great, that's easy. I'll just put the y on the other side. Okay, first let's go ahead and do this. We have dy is equal to y dx plus sine x dx. And now we have dy minus y dx plus, or equals sine x dx. And I don't have this y grouped with this dy. Okay, so the y and dy are not paired together. We can't integrate both sides. You can't do this. Okay, we can integrate side by side, and it is something that does carry through, right? It is a linear operator, but you can't do like a dy and a dx on the same side. It just doesn't work that way. So, yeah, we're not doing that. Okay. And also, these are mismatched. Okay, so it just isn't going to go. You say, wait, I know. I'll divide everything by y. That'll solve the problem. Okay, so if we have dy by dx is equal to y plus sine x, and I divide everybody by I multiply, right? We're going to multiply by dx and simultaneously divide by y. Okay, so I'm going to have dy over y is equal to, well, the y's, right? The y divides, so we just have a 1 dx. So far it's looking pretty good, but then we have sine x over y dx. That's not y by itself, right over here. So that don't work, all right? You can't do that. So great, that's not, we're going to solve this in the next section, all right? But we can't solve it right now. Okay, we're stuck with, that's a pretty equation. I wish I could solve it. Okay, next section. All right, so what you're looking for are functions that you can do that to. Okay, so here's a good one. Here's a dp over a dt, right, is equal to some kind of, I won't use the k this time. We'll say k is equal to 1. So we'll have p1 minus p, right? Kind of like a zombie apocalypse problem or something. Yeah, instead of a, we're just going to say 1 here. Okay, so we want to make the arithmetic easy, at least the first time through this. Okay, we get to some harder problems. It'll get hard enough, I promise. Actually, it'll get hard enough in this section. Actually, this problem, you'll grow to love it. So we're going to divide both sides, right, by p1 minus p, and multiply by dt. Right? So I divide, we get a 1 here, we multiply through, we're going to get dt. So we got dp over p1 minus p, and that's equal to dt. So wait a minute. Yeah, if only there was some kind of a class that you took where you could like break up this fraction somehow, like decompose this fraction. So we have 1 over p, 1 minus p, dp. I'm just going to put the dp out while I'm dealing with the fraction because we can multiply it into this whole thing at the end, equals dt. So like, oh, that's a partial fractions problem, isn't it? It sure is. So what we're going to do is we're going to say 1 over p, 1 minus p is equal to an a over p plus a b over 1 minus p. Right? Actually, I could put this on the other side and make this the left-hand side and that the right-hand side, because the first thing we're going to do to deal with this is we're going to multiply by p, 1 minus p, to clear the fractions, right? Because we don't like rational equations. We just multiply by denominators and not make them rational equations. So we have a 1 minus p plus b times p is equal to 1, right? We multiply through by this, right? These 1 minus p's cancel, so we're just going to have bp. The p's cancel, we're going to have a 1 minus p's. Okay. So we have a minus ap plus bp is equal to 1. Okay, now this is an easy enough problem, but I'm going to assume that we probably need some more work on partial fractions. So we're going to do what's called equate coefficients. Okay, so we're going to take all the constant stuff and set it equal to the constant stuff, and we're going to set all the stuff with a p in it equal to the stuff with a p in it. Okay, so on the constant, I've got a is equal to 1. Okay, it's a pretty easy equation. And with the linear term, right, we've got negative a plus b is equal to, how many p's are over here? None of them. 0. Okay, so since a is equal to 1, right, I can solve that pretty easily. We've got negative 1 plus b is equal to 0. So I think we can confidently say b is equal to 1. Okay, so our equation here, right, we have 1 over p times 1 minus p is equal to 1 over p plus 1 over 1 minus p. So this breaks down to dp, 1 dp over p plus 1 dp, and get a plus 1 minus p, and that's equal to dt. Back from a couple of lines up, right? Okay. If you still have to do a u substitution on this, you go right ahead and do a u substitution on this. Okay, so we're going to say let u equals 1 minus p, du would equal negative 1 dp. So there's going to be a negative sign here because of this. Okay, so we have natural log of p minus, right, because of this guy, 1 over, or no, not 1 over, more natural logs. Okay, so minus natural log of 1 minus p, and that is equal to t plus c. Okay, technically there's a plus c over here as well, because we integrated. We could have a plus c1 for this integration, a plus c2 for that integration, and a plus c3 for that integration. But what's going to happen, right? We're going to pull these to the other side, and we're going to have t plus c3 minus c2 minus c1. Well, we have a constant minus a constant minus a constant, and that's going to be a constant. So we're just going to avoid all of that mess and say we have t plus c. Okay. A lot of people have always asked me, like, where'd the constant go? We just prepare to abuse some constants. Okay, that is pretty much the subtitle of this class, is the abuse of constants. Okay, do you remember your rules of logarithms? Of course they do. Of course you do, like it was yesterday. And do you remember doing a log of a over b was equal to the log of a minus the log of b? Notice that's what we have here, right? So we're going to say that this is the log of p over 1 minus p, and that's equal to t plus c still. Well, why did I do that? It's because I only have one logarithm now. So when I want to take the anti-log, right, tell my pre-calculus class we unlogify it. So raise both sides to the same exponent. So we have, right, p over 1 minus p is equal to e to the t plus c. Well, e to the t plus c is e to the t times e to the c. And e raised to a constant is a constant. So if we're going to say that p over 1 minus p is equal to c e to the t. Okay, that's all the abusive constants that we're going to make in this problem. Okay, I'm just warning you that this is going to happen a lot. Okay, and I'll try to show it to you the first couple of few dozen times that we do it, that this is what's going on. Okay, and because we have to solve this explicitly, we can. Okay. So this is going to be p is equal to 1 minus p times c e to the t. Okay, go ahead and distribute that c through. So we have c e to the t minus p c e to the t. Okay, times c e to the t, and that was all equal to p. So push this to the other side, right? We're going to pull this over. So we have p plus p c to the e to the t is equal to c e to the t. And then here, notice that the p's are constant, or they're common, rather, not constant, they're common. So we have p, 1 plus c e to the t is equal to c e to the t. All right. And then this is p is equal to c e to the t over, let's go with c e to the t plus 1, because we got one more trick to do. Okay. And actually, the problem in your book stops here, okay? But I'm going to do one more step because when we do population problems, this is how you're going to say it. What we're going to do is we're going to multiply by e to the minus t over e to the minus t. So on the top here, we got nothing, right? We got these two cancel, and we just have c. So we have p is equal to c over, right? When I distribute this through, that's going to still be just a c plus e to the minus t. Right, that's the alternative form. And again, I know you all remember pre-calculus like it was yesterday, and we did some population modeling in that class with something that looked like this, where this would be the carrying capacity, right, of the system, and then we would do something this. And the really neat thing, right, this graph, we'll go over this more in DEs when we get to the application problems from here, but that graph looks something like this. Okay, it's called the Logistic Curve. Okay, and I just wanted to bring this around because if you look at the very earliest days of COVID, like during the first 6 months kind of a thing, this is how, right, this is the initial model for infectious diseases. And the countries that handled the disease, that handled COVID very well, pretty much had a curve that almost looked like this. Like South Korea was, I mean, the curve was beautiful. It's matched with this thing, like almost spot on. Okay, now we've had wave 2 and wave 3, and we don't have a constant population, right? We got people moving in and out, moving around, all sorts of complications. But when everything was first locked down, like you could look at countries like South Korea, and this was their curve. It was really, I mean, it's a horrible thing that we had the COVID, but at the same time, it was kind of a neat verification of a mathematical model. Okay, but we'll get more into that when we do some application stuff. Okay, though I think the next section, I think the section after that, no, section maybe after that, we do some modeling. We'll get into that. Okay, but or you could go back and remember your pre-calculus, like we all expect that you remember that flawlessly from 3 years ago. Okay. Of course you did. Okay. So let's see here. We're done with that. We're done with that. We're done with that. Next problem. Okay. I gotta admit, they put some pretty tricky problems in the homework for this one. To really talk to that guy. Okay, and this is equal to square root 1 minus x squared. Okay, dy is equal to 0. Okay, that's a minus sign, it's not an equal sign. Okay, so first thing I guess we could do is use some algebra to see if we can't make this work out. So I'm going to push this on the other side, but we're going to say this is dy times 1 minus x squared, right? That's this part. That is equal to, right, dx square root 1 minus y squared. Okay, and now it seems to like be a pretty simple way of kind of dealing with this, right? This is going to be dy over the square root 1 minus y squared, and that is equal to dx over square root of 1 minus x squared. Okay, now this is the point in the class where if we were face to face, I would ask you who remembers this integral, because it is an elementary integral that you were supposed to memorize out of Calc 1. I'll be honest, I didn't. Okay, but I'm looking at this like, hey, I've got some kind of an integral, and well, I'm going to have to take an integral here, both sides. Fortunately, they're the same one, so I don't have to do the same work twice. But I've got a square thing inside of a square root, which reminds me of saying, oh, this is a triangle. Okay. Just in case you were wondering if you had a chance to use pretty much everything that you've ever learned in math in this class, yes you will. Okay, so here we have is x, right? How do you do this? Right, here's Pythagoreans Theorem, right? And then what I'm going to do is I'm just going to subtract a squared from both sides. So we're going to have b squared is equal to c squared minus a squared. Which of these two forms, right? Which of these two equations, this one or this one, does this most resemble? 1 minus x squared. It looks like this one. Okay, so the c, right, that's 1. And then your a, right, that's your x. And you could either put it here or here. It's up to you. Okay, but typically if we could make a sign, S-I-N-E sign here, then we will generally do that. Okay, and that's 1 minus x squared. Okay, so sine of theta, right, equals x, or x equals sine theta. Dx is equal to cosine theta d theta. Okay. I'm going to do this the way that I learned it rather than the way that your calculus taught it to you, but they are equivalent. Okay, we could type in, right, sine theta here, sine squared theta here, right, and then go ahead and do that. Okay, I'm going to say that 1 over the square root of 1 minus x squared, right, 1 over the square root of 1 minus x squared. Isn't that the secant of theta? Okay, so what we have here, right, we have 1 over the square root of 1 minus y squared dy is equal to 1 over the square root of 1 minus x squared dx. Okay. 1 over the square root of x squared, 1 minus x squared here, right? That's secant theta. And then what's my dx? My dx is cosine theta d theta. That is equal to, right, secant of, I guess we shouldn't use theta. Okay, so I'll use phi for the same triangle, but within y's. Cosine phi d phi. Okay. What's cosine theta times secant theta? Isn't that 1? So here we have d phi is equal to d theta. Integrate on both sides. Okay, and we have phi is equal to theta plus c. Okay, what's theta? Right? Didn't we know that sine theta was equal to x? So if we take recall, right, we'll say recall sine theta was equal to x. So theta is equal to inverse sine of x. So same thing with phi. So we're going to say this is inverse sine of y is equal to inverse sine of theta plus c, or x plus c, x plus c. So can I just, no, you can't. I know exactly what you're thinking. No, it doesn't work that way. So we're going to take the sine of both sides to get rid of this. We're going to take the sine of both sides to get rid of this. However, right, this is going to be y is equal to the sine of the inverse sine of x, right? Inverse sine of x plus c. I should do it that way. That theta, that c is not inside there. It's by itself. Okay, because theta was inverse sine. C is innocent. C has nothing to do with any of this theta and phi stuff. C is just hanging out. Okay, so we have sine of this thing. So we have to take the sine of both sides. And I know that you guys remember, right? You can't just distribute this, right? It doesn't work that way. You can't say it's sine of this and sine of that. No, right? You guys remember like your sine of the sum of angles formula? Of course I do. I only had 3 or 4 years ago. I remember this absolutely. So this is, right, sine of the first, right? So sine cosine, I should have changed that, plus cosine inverse sine of x and sine c. Okay. I know you guys remember that. Okay. Let's see here. What were we doing with that? Oh, one of the givens, because this is actually an initial value problem. I neglected to tell you that. But our initial value here is that y of 0 is equal to 1/2. Okay, so we actually have to solve the c as we're doing this. Okay. Now, the sine of the inverse sine, okay, finally we catch a break. That's just x times cosine c plus. Now I need the cosine of the inverse sine, right? But going back all the way back up here, because we can use the same picture, right? Sine of theta was equal to x. So the cosine, right? The cosine of this angle is 1 minus x squared over 1. So this is going to be the square root of 1 minus x squared times the sine of c. Okay. All right. Just happened to work that out. That was nice. Okay. So we catch a little bit of a break. See, now the problem's easy. Right? A kid. It's not easy. So when x equals 0, y equals 1/2. So we have 1/2 is equal to, well, this term is 0, plus, plug in a 0 here, right? Plug in a 0, we just get the square root of 1. So we have sine of c is equal to 1/2. Where is this? What angle? Oh, hold on for a second. There we go. Okay, this is a note we're going to take here. Sine of c is equal to 1/2, just to make that known. Okay, but I could say what angle, right? The sine of what angle equals 1/2. Like, that was the first quiz I ever took in trig, and I still remember it to this day. So c is equal to pi over 6. Okay, and I know you have that at the ready. Like, just how could anybody not know this? Okay. So let's plug this back into our equation here, right? So we have y is equal to x times the cosine of pi over 6, right? Cosine of c, plus square root 1 minus x squared, and then the sine of c. The sine of c is what? Is 1/2, right? So since I know you knew, right? Sine of c equals 1/2. I know that you know that c was going to be pi over 6. So the cosine of pi over 6, again, I know you have this at the ready, right? As the square root of 3 over 2 x plus 1 minus x squared all over 2. And there you go. There's your answer. typically separable DEs. I've always drew kind of a sigh of relief when I've come across these because you don't require any kind of fancy techniques, and these are nice, and I won't say they're easy after the last problem, but at least you know where to start. You may not be able to finish, you might get stuck halfway through, but at least you have a starting spot so you can get some traction out of this problem. And they're usually not quite this awful, although all of the examples we're going to do today are going to convince you that they're all terrible, okay? But they're really not. Most of them are really tame, and you might have to do a little bit of a tricky thing with integration by parts or one of the other techniques of integration you've learned, but for the most part, these are all pretty tame as far as Calc 2 problems. Like, I really would rather not give you guys problems that had like, secant cubed in them or something terrible. But just to dash your hopes that this could have been an easy section, there's another problem that, again, I'm really going to have to talk to this guy about the homework. This is nuts. We got a dy by dx was equal to sine of the square root of x, okay, over the square root of y. Okay, so let's go ahead and, we could separate them, right? This is y to the 1/2 dy is equal to sine of x to the 1/2 dx. What could be easier? I mean, as long as you're looking at this side, like, oh, thank goodness. And then you look over here and you're like, yeah, that's delightful. I don't want to do that. Well, we can do it. Okay, so what we're going to do is we're going to let t, so why t? Because this is going to be a really fun problem, and I'm going to need a u and a v a little bit later. So we're going to say set t is equal to x to the 1/2. All right. So dt, every time you make a substitution in calculus, you have to take its derivative, and that is 1/2 x to the negative 1/2 dx. And now I am going to do it like your book, like your calculus book, like to do it, because that's the easier way to deal with this. And that's 2x to the 1/2, right? Because we multiply by reciprocal. Dt is equal to dx. Okay. So I'm just working on this half of it. Okay. This is not going to be so bad. This half, it's going to be a little bit of a slog here. So here we have sine of t, and then we have dx. Well, what's dx? This is equal to 2x to the 1/2 dt. And at this point, you're saying, I know you're not integrating that because I got two different variables, and you jumped down our throats in Calc 2 about doing this. And Calc 1, you can't do this. You're right. Fortunately, we know that t is equal to x to the 1/2. So this is going to be t times sine of t times dt, and that is equal to this integral over here. And again, we're just gonna walk this stuff through. If you remember what you're supposed to do when you had a polynomial times a trigonometric function, crying is not the answer. You say, integration by parts, of course it is. So we're going to go ahead and say, let u equal t, right? dv was equal to sine t dt, right? V is equal to negative cosine t, don't have a dt anymore, and du was equal to dt. So remember, we make a little box, right? And that's how we do this. So my integral is going to be negative t cosine t, right? That's this, minus, and then we have v du here, right? So that's going to be integral negative cosine t dt. Okay? And that's actually not so bad. At least it's not one of those integrals where you got to do it, twice and then swing one side over to the other side and then substitute and then divide. Remember these? E to the t cosine t. Remember doing that? Okay. Fortunately, it's not that one. Okay. So here we have negative t times cosine t plus integral cosine t dt, integral cosine. What could be easier, right? It's just going to be sine t plus, we have negative t times cosine t. Don't answer yet, we have a plus c. Okay. And then, okay, let's do the hard side, right? So that's just going to be y to the 3/2 and then 2/3, right? So just integrating y to the 1/2, add 1, and then divide by its power. Okay. So divided by 3/2, multiplied by 2/3 equals. Right? So this is just going to be y to the 3/2 is equal to 2/3. And then we have c plus sine t minus t cosine t. And then we could just take the, if we needed to solve it explicitly, I don't remember if the instructions said so, but probably. So we have 2/3, right? If I wanted to do this, right, if I wanted to multiply this through, what do you think 2/3 c is going to be? 2/3 of a constant is a constant. You'd be right. You don't have to say 2/3 c. It's just c. But I'm going to be lazy and not do any of this. And what was this? This was to the 2/3 power. Ta-da! So that's the thing. If you have parentheses, brackets, and then these things, braces. Okay, so you don't have to just use parentheses. This is the order it goes in. Okay. Delightful. All right. Honestly, though, a lot of these are not nearly as difficult as we're making them seem here. Okay, you do most integration by parts, you're like, okay, well, I just switch this and that, and then integrate both sides. But yeah. So at most, it's usually a partial fractions problem. And when I say partial fractions, I really mean kind of like the one we did first. Okay. One thing I will warn you against, and DE books are notorious for this. I hated these problems as a student. I hate giving them to you guys as a teacher because there's no closure. Okay. And what I mean by that is we have, like, say, y prime is equal to y e to the negative x squared. Okay. I'm going to check real quick if I have that still up. I don't know if I do or not. I do. Okay. So we're going to say this is dy over y is equal to e to the negative x squared dx. Okay. Now, you may have seen a little trick where you can, like, multiply this, but if you're going to multiply this one, you're going to have to multiply the other side. And now, best of luck, because now you've just shifted the burden to dealing with the other side of this thing. Okay. So this is a form that does not have an elementary function. Okay. So you can't integrate it. You can graph it. We can integrate it. It's a pretty famous integral. But this does not have elementary form as an answer. Okay. So there's no elementary functions. Okay, so we have natural log of y is equal to integral, because we can't integrate that really, right? From 0 to x of e to the negative t squared dt. Okay, this is another reason why I don't really like to do this, is because as a student, when I read this, I'm like, why did you change the variable? Because we could. Really? No, really? Like, yeah, that's the reason why. It has to do with fundamental theorem of calculus when you guys did that in Calc 1 of being able to change the variable to this thing. But yeah. Go ahead and do that. So we have, this is y is equal to e. Now, I guess we integrated on this side, so I guess we could have a constant here. So we could say a c e to the integral of 0 of x e to the negative t squared dt. And that's your answer. And we're like, that's the answer. Like, yep, that's the answer. You're done. Like that. It's an unsatisfactory answer. All right. I didn't get an answer. I just got a mess with integrals still in it. Like, that's how I always felt. Like, well, that's the answer. So I brought up a little Wikipedia here. I know, don't turn me into your humanities teachers. Okay, the math ones tend to be pretty good about detecting and stopping internet graffiti, but these are and they're integrals that you should probably try to recognize, because occasionally you'll get a teacher that's going to screw you up and you'll end up with something like this, and you're stuck trying to integrate this thing, and it just isn't a nice way to do it, so you're stuck with it. So I would try to at least familiarize yourself with some of these, so that you know that if somebody hands you like, oh yeah, sine x squared, you can do that. Like, no, they're just jerking you around. Don't waste your time trying to integrate this, because there's no way. Okay, you can't. We don't have Calc 1, Calc 2, Calc 3 methods to integrate this stuff. So I mean, they're all cool. Don't get me wrong, they really are. But yeah, don't look at this and say we're going to be able to do this, because you aren't. And that's fine. Nobody can. Okay, seg function. Okay, it's kind of cool. So yeah, this thing. Again, yeah, we can do some of them, but yeah. I don't like to give these to you for homework. I certainly don't like to give them to you on quizzes, but you should be aware that there are functions that you just can't do them. Okay, and sorry. But yeah, you're not going to see too many of those out of me. I'm not trying to do this to you. Okay, but that's separable differential equations. Like I said, most of the time these are a lot tamer than what the book has shown you. But just to recall that you might have to do an integration by parts. You might have to do a crazy U sub. You might have to do a trig substitution. Not so much of the trig substitutions, but integration by parts are pretty common to throw integration by parts integrals into stuff like this. Okay, so just to warn you. But like I said, despite all my examples tonight, these are usually pretty tame. Okay, so I'm going to leave us with that, and we'll talk about how to solve linear differential equations next time. Okay.